Hello and welcome back to Calculus 1. This is related rates part 2. So what we did before was define that the related rates are these formulas that relate derivatives. Those derivatives measure how fast whatever concept we are measuring is changing. So change in time, whether it's area or distance, perimeter, and also volume. We haven't dealt with volume yet. Now, I want to go back to this airplane problem and note that when you are when this is the situation you're observing, these two planes are both moving in towards the airport, and the distance d is decreasing. So we had 6 variables that we had to consider, and one of them was the distance between the two planes, and one was then how fast that distance is changing. And we were able to calculate. Now, what I want to do is take a look at a very similar problem. We don't have to put the numbers in, but at least we can talk about the concept and the equation. So let's put a house of some kind over here. Here's the roof. And we're going to put a gutter over here, and that gutter has leaves, and then Mark is going to put this ladder up 25 feet ladder. So this is a house. It doesn't have to be Dolly house, so let's do that. There we go. And the chimney, you have to have a chimney, right, with the smoke going. Perfect. There we go. All right, so you have a ladder against the wall, and it's a 25 feet long ladder, and then you're going to have Mark over here standing on this ladder cleaning these leaves. We'll put a top hat on this guy. Well, it's now like a cowboy hat. There we go, fine. Cowboy hat, that's okay. Well, if you put a cowboy hat, then you have to put a pistol and all that stuff, right? Whatever. Anyway, so Mark is there cleaning, right, the gutter, and his troll friend Joe, I don't know how much of a friend he is going to kick this out. The bottom of the ladder. It's going to kick it out. And we all know what's going to happen here, right? A YouTube post. So, what is the physics of this? When you look at this picture, you have the height y and a distance x. And you can immediately write that right triangle Pythagorean theorem. There is nothing different except this time this 25 feet is no longer variable. Now this 25 feet is the fixed number because the ladder is 25 feet long. So when you kick out the bottom part of the ladder is going to go like this and like that, and it's always going to be 25 feet long. It's not going to shrink, right? The mark is still going to hit the ground, but the ladder is not going to change its length. So earlier, when you had two airplanes, this distance d was decreasing because both planes were getting closer and closer and closer together. So this d became smaller and smaller and smaller and smaller going in. But now, this hypotenuse distance to 25 is fixed. So that needs to be there in your equation. Now, if you take the derivative of this in respect to time, you get your 2x dx dt plus 2y dy dt that's a 2, equal to 0 on the other side. Because 25 squared is 625, but the derivative of constant is 0, so I don't even care what that is. And now, what do I know? Well, we can cancel 2's, right? Dividing both sides by 2. You are going to get x dx dt plus y dy dt equal to 0. And because I have this, now, if you have numbers, yeah, go ahead, compute things, right? But the most important part of all of these problems is understanding what each variable represents. And when you move y on the other side, you get x dx dt equals negative y dy dt. You divide both sides by y. Y is a length up the house. It's not 0. So x over y dx dt is equal to, I'll put negative dy dt. Now, look what's happening. You have your dx dt, and you see that it's pushing to the right, making this distance x longer. Should be a positive number, right? Then we also have dy dt, which is going down because Mark is going to hit the ground. But look, his y is decreasing in length. So you're going to get a negative number for his velocity because he's going down, closing the distance between the 0 and whatever height he was at the beginning of the problem. And then you just have x divided by y because that's the mathematical relation that came up with all of this stuff, right? So now, given the distance in x, which you can measure, right? Even if you are watching a YouTube video of something like this when Joe kicks the ladder out, right? If you have any reference on the screen of something, how tall it is, and usually you can just approximate these things by taking that the person is, right, that Joe, the guy who kicks out the ladder, is 6 feet tall. Then you can just compare the height of that guy with this height here for x, and then you have the heights, you have the length x, right, and then you can approximate the height of the house using that one as well, and you have your x and a y, and then you can actually calculate, frame by frame, the speed as well. You can easily calculate how fast the top of the ladder will go down. So it's pretty much the same problem as the one before, except this time, right, that distance d was constant, so it was way less calculation and way less mess than what we had previously. All right, one more two-dimensional problem, and then we're going to move to 3D, which is volumes. But for this one, I don't know if you have watched the SpaceX launches, Falcon 9, and I mean all of them. If you haven't, again, why are you in this class? Those things need to be something that should be automatic for you, right? Because as engineer of whatever calling, space launches are technically all feats of engineering together: material sciences, chemistry, physics, obviously mathematics, and then you have all of the electrical, mechanical engineering, civil engineering for all of those structures that launched the rocket and barged for it to land. Like, every single feat of engineering is there, has a huge economical, obvious impact. So again, if you are not watching those things, you're not interested in those things, I don't know why you are in STEM. You are probably in the wrong field, because literally every single concept of every single major that you guys is a part of the whole thing. So you can find the part in there. Now, the launch is very interesting because it needs to be recorded by the camera. And that camera, you can have a Joe standing right to the side with the camera, sufficiently far right away, and then hold the camera and then get that shaky footage right going up. Or you can engineer a little mechanism with a servo motor in it, which would be programmed with a function that will get the information from mission control on, we'll see what parameters, and then the programming will give the signals and enough input for the servo motor to uh, turn the camera and do it. So let's figure out how this thing works. So I'm going to have a launch pad over here. I'm going to have this little trench here. I'm going to put the camera there first. Let's put the camera at the 0 angle at the beginning. There we go. And over here I'm going to put the rocket. There we go. Look at that rocket. And that rocket is going to be launched straight up. There is a height there. This is going to be some kind of fixed distance. Let's put 1,000 feet in there, for instance. I can do this in meters as well, but whatever. Put 1,000 feet over there. And now the camera is recording straight. Now there is a lens to that camera, right? So it's always using the shot, right? But we are not going to worry about these two lines. We're just worrying about this one line. And then as the rocket goes up, the camera is supposed to rotate with angular velocity omega. And then the camera will record there and there and there and there, right? And it will have all of these angles because as you rotate the camera, as the rocket goes up, the camera is going to record this thing. All right, so I'm just going to make this line straight over here. Perfect. There we go. So now I'm going to just erase all of these in between lines and leave the bottom line and leave the top line. So we have a right triangle again, right? We have the right triangle, but this time it's the angle that it's important at which the camera is recording, which means finally we get to use trig, not just the Pythagorean theorem. We get to use trig because we have an angle that it's important in there. Remember, it is for all we want to know, right? So we can program in the controller that will turn the servo motor on and off and give it the speed and all that stuff. All we want to know is the angle at which the camera needs to be pointed at so that the rocket is in the middle of the shot. That's what we want. So because we want that angle, we are going to use trigonometric function now. And we have the two sides given, as you can see. We have that h, which is the height of the rocket. When the rocket is still not launched, right, it's 0. And then it's going to be 100 feet and 200 feet and 1,000 feet and 10,000 feet, right? So that is going to go up. So we always know age because we know where the rocket is. And we have 1,000 feet. So which trigonometric function would be a good function to use when you have these two pieces of information?
Inverse tangent.
Well, let's use the tangent only. But yes, tangent, because we have opposite of the angle and adjacent of the angle. So opposite and adjacent is a tangent. So we'll use tangent theta is height h divided by 1,000 feet. Good. And what I want to study is I want to study this angle eventually. So now there are two ways. You can go with the inverse tangent route, or you can just go with the tangent route. And we'll see. We can do both. I mean, if you take the derivative in respect to time, the derivative of tangent is?
Secant squared x.
Very good. And then we have to follow with d theta dt, because we took the derivative of theta in respect to time. So d theta dt is equal to, and over here you have 1 over 1000, and you have dh dt because the derivative of h is 1, and then again the chain rule. And now you can fix this. You are interested in d theta dt, which would be 1 over 1000 times 1 over secant squared theta times dh dt. Now, angle, change in angle in time. If this is change in position in time, and we call that velocity, then change of angle in time has to be angular velocity. This thing over here is your omega that you want. That's the one. So we have to clean up the well, actually, let's do this immediately. Omega, right? That's what we want. This becomes cosine squared theta over 1000 dh dt. Cosine squared, because secant squared from the denominator would go up as a cosine squared in the numerator. And all I need to do is to get rid of the pesky cosine squared, and we are done. Now, the pesky cosine squared is easy to get rid of because you have a triangle up there. You can read the cosine and plug the variables in. Once you have all of those calculations, you have an equation which computer science major is supposed to plug into the software, and then electrical engineer is gonna work with the controller and a servo motor and so on. Mechanical engineer is going to put all of the gears and everything together. There is no one person doing all of these things. Yeah, you can make a little project and spend time, but you have teams. There is electrical team and mechanical team and computer science team, and they all work together, and each one has to know a little bit about the other ones so they can interface together and put the whole thing together. But we're dealing with computer science here now. You would call it math, but you're developing the formula that you are going to plug into the controller, so it's computer science. Cosine squared. So what is my cosine up there? Well, I have this length over here, and this length is h squared plus 1000 squared. I hope you understand that that's the length of the red line and the hypotenuse. So the cosine is adjacent over hypotenuse, right? So cosine theta is adjacent over hypotenuse, and because this thing was squared, the whole thing over here is squared. So now we're going to plug this in and get that our omega is 1 over 1000, and then you're going to have your 1000 squared over h squared plus 1000 squared, everything squared, dh dt. This one cancels, and here is your formula: 1000 over h squared plus 1000 squared squared dh dt. Yay. Height of the rocket, known at all times, right? What is this? dh dt. What is this?
The change of position over time velocity.
Velocity of the rocket. Yes. So, height of the rocket in respect to the ground, speed of the rocket. Now, if you watched any of the SpaceX launches, they put those two right there. They tell you how high up the rocket is and how fast it's moving. Both of those numbers are known, altitude and speed. They are right there. If you go on YouTube and watch any of those because you missed it, and now you know that you should catch up, obviously, you will find those two numbers. And what do I get from there? I get the angular velocity, which is how fast I need to turn the camera. So now, when the rocket launches over here, this angular velocity is going to start spinning the camera slowly, right? As the rocket is going up, the shot changes like this and it goes higher and higher and higher and higher because right here, right, there is a gearbox with a servo motor in it, and then the information that the mission control is giving to the controller is speed of the rocket and altitude of the rocket. The computer science, right, the software is computing the angle of what the angle should be. Now, the spin of the servo motor has the correlation between how much electricity you supply to it and for particular angle for it to turn. So when you put all of those things together, right, the simple input of the height and the which is a constant input, right? The software constantly computes what angle it should be, which is fed into the power supply, which supplies certain amount of voltage to the servo motor, and servo motor turns exactly for that angle that is calculated through the formula. You cannot do any of this without computer science, without mechanical engineering, electrical engineering. Those are the base ones. Then you need material engineers, and you need packaging engineers, and you need all other engineers, right, to make all of these things. Plus, you need people that understand cameras and focus the thing, and like just to make a shot, just to make a perfect shot of the launch. That's not even making a rocket, right? So that's something that simple concept, we can understand it here, but it was a good exercise for us to see where we can use the trigonometry when you are using these things. Cool. Now, well, do you have any questions?
I believe you said you'd also do it with the inverse tangent, or were you saying you can do it with the inverse tangent?
You can, right? If you have that your tangent theta is equal to the what was it? Was it 1,000 over? I forgot. Age over 1,000. Age over 1,000. We'll apply inverse tangent on both sides. You get your theta is equal to tangent inverse of age over 1,000. Now, if you hit both sides with the derivative in respect to time, you get your d theta over dt on the left, which is your omega. And on the right-hand side, tangent inverse, this is usually hard for students. I'm not sure why, but it's one formula. And then you have to convert it now into a function, because this is a function age over 1,000. That's going to be f prime over 1 plus f squared as is. So the denominator is 1 plus age over 1,000 squared, and the numerator is just the derivative of this, which is the age dt over 1000. Well, actually, I can put 1 over, let's do that better. 1 over 1000 dh dt. So now, when you multiply top and bottom by 1000 squared to kill the denominator fraction of 1000 squared, you get your omega is equal to, see, 1000 will cancel on top, the other one stays, so that's 1000 dh dt that stays on top, divided by the bottom is 1000 squared plus h squared. That better be the same as the formula we had before, otherwise I'm going to flip out. Yep, it is. Oh, I forgot. No, that's so good. Right, so it's equal to, I have an extra squared over here. dh dt. Did I lose something?
Don't you have that extra squared because of the Pythagorean theorem?
They have to come up to be exactly the same. They can't be different times dh dt. Now I have this one squared from before. Is that an extra thing that I... So 1 over 1000 over h squared plus... What the hell? It has to be the same. There's no doubt about it. I just have never done the problem using the inverse tangent, but doesn't matter. It has to be the same. So we have a tangent inverse. That's going to be the derivative of the inside on top. 1 plus this thing squared. When I multiply by 1000 squared, this one cancels, this one cancels, and I am losing this.
You
What?
plug that value for the secant squared, though. That's why the extra squared comes out, right?
Yeah, but it doesn't matter which way you do the problem. It has to be, the formula at the end has to be the same. Right? The formulas look the same except for the everything squared.
Yeah,
So,
but I'm agreeing with the first equation more. That's what I'm saying.
well, I'm see, the problem is that I don't see what's wrong. That's the issue. It doesn't matter which way we solve, we have to get the same formula, and we are not. So we should be able to do the inverse tangent and solve the problem and get the same thing. So I have the h over this. Okay, I'm just going to go through all of these calculations just in case. So tangent theta is secant squared. Secant squared turns into a cosine squared. Cosine squared is going to be over here. So Pythagorean theorem, because we need a hypotenuse for cosine. These two are the cosine. So adjacent over hypotenuse, which is 1000 over this. And because it was a cosine squared, we have a square. So now we plug that in. And then 1 over 1000 in front. And that's just going to kill, and that square stays there. What the hell? Tangent h over 1000. And when we take the derivative, it's a chain rule. So we have to use this one. That's the formula. So we have h over 1000. And the only thing that I'm losing is still, I mean, it's not the formula to have this, obviously. Yeah, I have to look into this, and because I'm so puzzled right now that it came out to be different, and I can't find the mistake in any of the two. What the hell? I'll have to look at this later because we still have to talk about the volume and stuff. I'm just going to put a big fat question mark over here, 3 of them, and put this in as a reminder. So I'll take a look at this, and then if I figure out what happened here, yeah, I have to do this all from scratch, and I don't want to spend any more time. But the equations have to be the same. The way you solve the problem should not matter, one way or the other. You have to solve the same. So I'll take a look at that, and hopefully next week we can fix it. But it has to be the same. Okay, so that's the two-dimensional problems. Now we're moving to the 3D volumes. Now, volume V is the amount of space, the three-dimensional space that the object will occupy. It is very simple to memorize volume formulas. A lot of students are okay with area of the circle, circumference of the circle, area of rectangle and square and triangle, right? The perimeter of those. But then when we start talking about area, all of a sudden people, I ask, what's the area of the cone? And it's just crickets on the other side, right? So let's talk about volume in general so that you know all of the volume as you go. So the volume is divided into these 3 categories of objects. We have, in the first category, we have those prism-like objects. There will be like a box like this, right? A rectangular box as well. It's the same thing. A cylinder like that, like a soda can. All of these objects, and we'll see how these objects are different than the other ones in a group. All of these objects have the formula for volume of base times the height. So this will be your height of the object. And this is the area of the base. So the difference between these objects is, well, what's your base? Oh, we can have a triangular prism as well. It has to have a triangle on top, like that. So what is your, I mean, you can put the trapezoid, you can put literally whatever. So all of these objects have the height, which is just a number, but then the base is the one that determines, right? Is a square, is a rectangle, is a circle, is a triangle. So as long as you can compute that area, you can compute volume easily by multiplying it by a height. Then we move to the second category, which are cones and pyramids. Call them spiky objects. So you have a cone, like the ice cream cone or top of the witch's hat or whatever. You have your pyramids, whether those pyramids have 3 sides, 4 sides, 8 sides, whatever, right? The important part is they have this spike on top. And their volume is just 1/3 base times the height. So again, area of the base. So if you are able to compute the volume of any of the objects in the first group, then just multiply that by 1/3 if it has a spike on top. So cones and pyramids and all of that. And its own category, our heavyweight champion over here, sphere. V equals 4/3 pi r cubed. You just have to memorize that. It doesn't belong. It's a special object. It's a very special object. It has a very special property, which we'll run into eventually. And sphere does not fit in any of the two groups. You're done. That's it. That's the story of volume. So now if you say that you don't know a volume of a particular shape, you're really embarrassing yourselves, because it's not that difficult, as you can see. You categorize all of the objects in one of these three groups, just memorize the volume for the sphere, because, come on, it's a ball, right? It's a basketball and tennis ball and, right, all of that stuff. And you're done. You have all of your volumes straight. So now, if you are talking about the piston for mechanical engineering, let's say for some reason you're still engineering the gas-powered cars, it's this one, right? And you let the snowball roll down the hill, let's say, right? It rolls like in a cartoon movie, right, where it picks up snow and grows in size. It's gonna start with a little snowball and get to the giant snowball, which I don't know, slams into the house or a person or whatever in a cartoon, right? So we are going to have all of these objects expand or contract, or they're going to have, you know, something happening. So let's start with the probably cheapest and easiest concept. These are the problems that I, you know, assigned to students who want to really understand and like this, and that is, you have a soda can of some kind, right? And you are wondering if you are to, right, put a straw inside and take a sip on that straw. So that straw is gonna go inside all the way down to the bottom, and you have some liquid inside this can. When you take a sip, the liquid goes down. That should not be a new concept, all right? So what is a sip? Sip is change of volume in time. That's what the sip is. Now we can calculate the average sip, not calculate, but get the average sip. I'm just gonna go quickly to Google. Average sip size. Let's see what we get. 12.75 milliliters for men and 20 what? Oh, different values for a normal sip size have been reported in the literature. So average of 12.75 milliliters for a single sip of water, with a range of 4 to 29 milliliters. Someone else reported 25 milliliters for men and 20 milliliters for women, and then keeps decreasing from there. I'm just gonna go with the 1275 average. I don't care. But this is something, right? And then in whatever it takes you a second, let's say, to take the sip, right? So there is a volume of how much liquid, which is 1275 milliliters, but then you sip that over, let's say, 1 second, right? That's how long it takes to transfer that one sip from the container to your mouth. So it is a very simple idea of figuring this out, and all you just say is, okay, the volume is area of the base is pi r squared times the height of the can, because the height of the can is known, right? And the radius r of the can is known. Okay, now, it is very important, and I have to write this in blood over here. Know which letters are variables. Others are constants. You have to be very careful with this. If you have a soda can that is full all the way to the top, then the volume of the liquid inside is equal to the volume of the can, which means you can use the formula and compute the volume of the can. Volume of the can is printed on the can, and you know how much liquid it contains. Now, you also know the height and the radius of the can. This is insanely important, guys. When you start sipping, radius never changes. Because when you sip from the straw, from the soda can, let's say, the can doesn't become smaller in radius. The can stays the same width. The can stays the same height, but the height of the liquid decreases. So what is my variable? The only variable here is height of the liquid. And radius is constant. I don't know how to express how insanely important this is. Guys, when you are taking derivatives, when you take derivatives, the constants, you don't take derivative of them, you copy them, right? And you will take the derivative of age. It's the difference, the physical situation of what is happening is the difference between a single derivative or a product rule. Now, we'll see in the next example when things turn differently. But now, when I Google can size, soda can size, I see that, oh, great. Now this one is given in inches and the other one is given in milliliters. Can I get this in metric? Soda can, and now they give me different ones. How many? What's the standard volume of a soda can? $335 milliliters. Okay, 335 milliliters. Now I have to chase that over here. Metric. Okay, 335 is 58 milliliters diameter. Nah. Diameter, D, is equal to 58 millimeters, which is going to be radius is half of this, which means 29 millimeters. Now, I'm just going to call that 30 millimeters. Yeah, whatever. Doesn't matter. 29 is fine. All right, so now I have the volume is equal to 2 pi 29 squared and then height. I plug that number in. because the radius will never change, no matter how high, right, how tall the liquid inside, how high it is, at which height, whatever. No matter at which height it is, the radius stays unchanged. So what I have here is actually 29 square. I should have changed this to 30, because if I change this to 30, then this is easy to square. Okay. So that's going to work out to be 900 pi h. And when I take the derivative of it, dt gets me the volume over time is 900 pi dH dt. So now you see that because they're directly proportional, when as you're taking sips, meaning you are taking the liquid out of the container, the height goes down as well. And you know, this is a good thing to bring next time you're out with your friends and so on. See someone drinking from the straw from a can, you can immediately work this out. Show them who's the boss. All right. We have now the equation that tells you how much, and these are the sips, the liquid coming out, and this is the height of the liquid in the can decreasing, being related by this never changing radius. So now when the numbers are given to you, right, you can work out your sip over here, and the sip is going to be obviously negative 1275 milliliters. And this is already in millimeters squared. Remember, you took 30 millimeters and you squared it. You get your dH dt, which is the height. So you have all of these. You have all of these things. You can work out. You just plug in the numbers and you get whatever you need, right? If you are measuring how fast the height is decreasing, you can get the size of the sip, right? And then the size of the sip. I don't know. Criminal justice just popped into my mind because for some reason, right? Since that website said that the male has 25 milliliter sip and the woman had 20 milliliter sip, and let's say there was one sip taken out of the soda can, right? Then how much was taken, right? I mean, you can have fun to figure out where all of these concepts can kick in. I can just do the problem the way that, you know, the boring way, say you have a cylinder, right? And then the height of the cylinder is going to decrease or increase. Right? It's not as much fun as when you actually have, you know, soda can with liquid inside, and then you're figuring out how much does it go down as you are drinking. All right, let's open the gates of hell. Cone. Now, why would I say open the gates of hell? Because cone is a very interesting creature. Whether you want to look at the, let's say, you know, when you eat your ice cream, and if you took your sweet time, usually inside the cone, you're going to have melted ice cream, which is liquid, right? You can sip that as well, but it's not sitting in a cylinder. It's sitting in a cone like this. So I hope you guys see that if this is the level of the melted ice cream inside the cone, there's also those water coolers that have those conical cups next to it that you can never get out of the dispenser. When you take a look at the level at which you have your water or ice cream or whatever, at this level, your radius is R1. At this level, your radius is R2. At this level, your radius is R3. And you also have the height 3 and the height 2 and the height 1. So now you see that both R and H are variables. And when they are variables, then you have the product rule in the cone in the cone equation. Remember that the cone equation and the cylinder equation are the same, except cone has times 1/3. So there is no difference in computing these two in terms of, oh, one is harder than the other until you actually do the derivative. Because for our soda can, R was fixed at all times. It was not a variable. Therefore, I wrote this on a side because you always have to be very careful about that. And because R was a constant, always the same radius, I was able to actually plug that inside the formula and just treat it as a 900 constant, drag it around. But now for the cone, radius is no longer a constant. So we will have the product rule. Now, the problem that I usually present to students is that you have some conveyor belt over here, right? That has sand or corn or whatever coming in. And then when that starts hitting the ground, it starts creating these cones. Because it always falls into the conical, right, structure on the bottom. So you see that this cone is growing in height, it's growing in radius, and obviously if you wait long enough, then the cone is going to be as tall as the conveyor belt is, and then it's going to start piling up stuff on it, and then eventually, you know, let's say a $1 million piece of equipment is broken. Well, you say, well, that's easy because you can just create a shutoff. Yeah, but let's talk about the engineering of the shutoff, because, you know, it's stone, it's gravel, it's corn, there's a lot of dust, so you can't put a light sensor at some level because very quickly that lens is going to become dirty with dust and so on. So you can't really do that. Maybe you have the issue with, or the bird flies through and interrupts it and shuts off your conveyor belt, and you are only on the first stage of filling it, let's say. So bird flew by. So there are a lot of reasons why you do not want to use photo sensors to make a cutoff at the specific height. Okay, what else can you do? Well, maybe you can suspend some kind of probe, and then when it touches the probe, it sends signals and shuts it off. Yes, that's a maintenance. That's, again, something that breaks and so on. Can't you just have computer science write a code, right? And then knowing how much volume is coming in, because we have that information, right? We can eventually code something that will shut off the system when the cone gets up there. So you don't have to pay a worker whose only job is to stare at the pile, and then when it reaches certain height, if the worker didn't pass out of boredom or something and not sleeping, the person is going to press the button, right? So that's not very efficient for business either. So you want to make some kind of system that will work this out. Now, again, you know that the volume of corn or gravel or whatever is coming in at specific rate, which is dV dt. So we need to work out the volume of the cone, which is, it's a spiky object, base times the height. Now, area of the base, that's a circle, so pi r squared, that's a joke. And now you have your volume of pi thirds r squared, and then h is the height of the y that is changing. Now, here, written in blood, both are variables. Very different than the previous problem where r was constant. Now r is changing as well. And you can see that, right? The radius was little, then larger, then larger. So the radius grows the more stuff gets onto the pile, and the height grows as well the more stuff comes to the pile. So now all I need to do, all, right, is to compute the derivative of this in respect to time, because I want to know how fast is the radius changing, because that's my space on the floor. How fast is the height changing, because I don't want it to reach the conveyor belt, pile stuff up and break it. And I also want to know how much volume, right? How much volume per minute or hour or whatever is coming in, because eventually I want to shut off the machine so it doesn't break, doesn't overfill, and so on. So I'm taking the derivative in respect to time. And here it is, product rule. Okay, product rule. Both of these are variables. So dv dt, right? Derivative of v is 1, and then follow with the dv dt in the chain rule. Copy your pi over 3 constant, and inside copy the first, derivative of the second, plus copy the second, and then derivative of the first. When I take the derivative of h, I have to follow with the dh dt. When I take the derivative of radius r, I have to follow with dr dt. And now, you know, there's not much you can do here. You know, literally just rearrange this, and you have your what we call related rates formula: pi over 3 r squared dh dt plus 2rh dr dt. This is your related rates model. And this related rates model is exactly the same for every cone that you can possibly think of. But it has a lot of variables. It has dv dt, has r, has h, has dr dt, and dh dt. It's 5 variables. And usually it's this one that it's given, because you know how much stuff is coming in. And usually this is what you are looking for, because you want to know at what rate the height is growing, because you want to program it to shut it off. It's dr dt that is a problem that we want to get rid of, because you know r and h, we can measure those, right? You can measure the height of the cone, you can measure how wide it is, and so on. So all of that stuff is easy, not a problem. But what I need is to get rid of this dr dt, because generally we don't care about that. I mean, it's still important. It's in a formula. Obviously, it's important mathematical concept that is, you know, about the whole thing. But the thing is that when you look at the dr dt, that's how fast the radius is growing in time. It is the area on the floor, right? So what is this circle, and how big that circle gets over time, technically over time. Okay, so now usually for the cone problems you have another piece of information, which is relation between the height and the radius. So they might say that height grows twice as fast as radius, or something like that, right? So problem may give h grows twice as fast as radius. Now, from a center, or 3 times, or at 2/3, or 5 times, whatever. So they're going to give something. That equation can be transferred into h, in this case, h equals 2r. And from there, you can differentiate this equation and you get dh dt is equal to 2 dr dt. And here are the missing pieces that you can plug in into the formula. So let me put the star over there, and say plug in and replace unwanted variables. What do I say unwanted? Because you're either looking for heights or you're looking for radius. Usually dv dt is given because that's right the amount of stuff coming in. So if they want to know about radius, then you change all of the heights into radius. If you want to know about the height, then you change all of the radius into height. So when you take a look at our equation, dv dt, what you have over here is pi over 3. And now, let's say you want to get rid of the radius. You have your r squared. That's going to be h over 2 squared. And you have your dh dt plus 2r is h. 2r is h, and then you have another h, so h squared. Maybe I should say h times h. And then you have your dr dt. dr dt is 1/2 dh dt. So let me just put this. This is r dh dt plus 2r h dr dt. So all of these variables are replaced with new letters. And what you get is dv dt is equal to pi over 3. And what do I have here? The first one is h squared over 4 dh dt plus, and the second one is h squared over 2 dh dt. Hey, I can just add those fractions, right? It's the second one times 2 for common denominator. That's a joke. dv dt is equal to pi over 3, and then I have 3h squared over 4 dh dt. The 3 will drop, and I have my related rates model where r is eliminated. So we have pi over 4 h squared dh dt. You can measure this one. This one is given on how much stuff is coming in, so you can calculate the change in height. If you wanted to calculate the change in radius, then you would be replacing this one and this one with their r equivalents, and you would do the same calculation. And all you need to do at the end is to plug the numbers, right? Plug in and plug in the number, whatever is given in the text, and you will have your answer, because it's the basic equation. All of the problems are done the same. Consider geometry, put the formula down, differentiate the formula in respect to time, see if you need any additional numbers or things to put in, and then you're done. That's all it is. It's gonna take some time for you guys to get used to all of these calculations, but right, eventually you will get there. In the book, shrinking isosceles triangle, expanding the circle, shrinking circle, balloons, that will be the sphere problem, right? Spherical balloon. Shrinking cube, expanding a rectangle, melting a snowball. And they're asking you about the surface area of the snowball. Why? I will never understand it, because you can't even paint it because it melts. I have no clue why would you want to know about the surface area. But the surface area for the ball is you just take the derivative in respect to r. Over here, it's a very special object. Where is the thing? Here. So the surface area, if you run into it, it's just going to be 4 pi r squared. If you take the derivative of this in respect to r, the 3 will cancel 3. It's actually related to why circle and spheres are very special objects in comparison to all others. So yeah, there's that. Time lagged flights, and then you get into this. And there is a piston. Problem 33 in a textbook has a piston compression, right? There's fishing and a whole bunch of stuff. There's the ladder problem that I worked on, number 41. And then they have some really, really interesting problems later on. Problem 47 for the viewing angle for the theater, if you want to build one in your house. The problem 57 for filling a pool. Now, if you really want to impress me, it's going to be a problem 62 with a Ferris wheel. That one took me an hour to figure out when I was a student. So, and another scary problem 63. So, most of the stuff we did today is considered easy. Cone problem is considered spicy. So if you are going to look into anything that has a cone or that viewing angle thing, maybe even the pool, all of those would be, labeled as spicy problems. But then the Ferris wheel and this half barrel thing in problem 63, that's extra spicy, like 5 chili peppers on it, right? Try to figure those out, and hopefully you understand that because you are STEM, this is how you make money. This is what you chose to do to make money going down the line. So this should be your favorite and best section of all right now that we covered so far in calculus. We'll do one more example, and that will be it. I'll talk about this melting snowball, even though it's a ridiculous concept of looking for a surface area. Why? But anyway, so a spherical snowball melts at the rate proportional to its surface area. A snowball. I don't know why they had to say a spherical snowball. It's worked into the name, ball. We know what the ball is. So why put a spherical snowball? Can it be a rectangular snowball? Whatever. So a spherical snowball melts at a rate proportional to its surface area. Show that the rate of change of radius is constant. Oh, this is a proof. Show that the rate of change of radius is constant. You know what? dr dt is constant. I don't want to spend 30 minutes spelling rate of change of radius. If you didn't pick up that by now, I mean, good luck with the rest. Rate of change is always the derivative. We said that 2 hours ago, and we've been using it for the 2 hours. At this time, it's not up for a debate. dr dt is change of radius in time. So rate of change. All right, so we have our surface area, which is, well, I'm just going to call it S, or no, area, A, as 4 pi r squared. That was something that we talked about before. I have it up there in the list of formulas. And now we also see that the snowball melts at the rate proportional to its surface area. Now, this is a tricky statement, right? Because we are not looking for change in area. We don't get to differentiate right now. We first have to come up with the mathematical formula, then we can do the derivatives and the engineering. So we have to figure out what to write here. Now, when something is proportional, you would say y is proportional to x. This is how you write that y is proportional to x, because you put this y over x as a ratio, it turns out to be some constant k. So you know that you have the screens and the ratio is 16:9 for the wide screen, but then you can have a 55-inch TV, you can have a 50-inch TV, you can have a 70-inch TV, you can have 34-inch TV, right? Any of these diagonals. That's just the same, but the aspect ratio is always staying the same, right? The bigger the screen, it doesn't matter. This length is always be 16 units and this length will always be 9. And then diagonal measures, right, this way. So when you say that something is proportional, then you have that k worked into it. So a snowball melts at the rate proportional to its surface area. So the rate of melting of snowball is proportional to this. A snowball melts at the rate proportional to the surface area. So now I need dv dt. Well, the volume is 4/3 pi r cubed, and when I differentiate that, we get dv dt is 4 pi r squared. Plug that in there. 4 pi r. Oh, I forgot my dr dt. Holy nightmare. There we go. 4 pi r squared dr dt is equal to k 4 pi r squared. Push, push. There you go. Constant rate. If you're able to read, right, and just replace the words with mathematical concepts, then it just flows. It just goes. And don't be afraid to read problem 15 times if you need to, right? Because these things take time to get used to. You have never dealt with the problems like this before, but I hope you've seen the scope and how powerful these problems are for the design and understanding things around you. Questions, concerns? And as I said, if you want a challenge, right? When you think you know it, you think you understand it, go spend a few hours on those problems 62 and 63. See how far you can get. As I said, it took me about an hour to figure out problem 62, and I had one student who said I figured it out in 30 minutes. Awesome. Perfect. So yeah. No questions?
I think I'm okay.
All right. Well, I'm happy that I'm that clear. In the end, this is my favorite stuff. I still have to go back and figure out what happened with that inverse tangent thing, but we're now going to take a break, and when we come back, it will be 4.1 on minima and maxima of a function, right? So minimum, maximum, and all of that stuff. So chapter 4, application of the derivative. So let's take a break, and then Yep, we'll be back. So I'd say like 10 minutes or so at least.